Is from Ukraine today. Volodymyr's been doing some awesome work in a number of different ways. We've talked about Viper IDE, which I'm not sure you're going to cover today, or nope. We'll talk about Viper IDE another time. Again, I'm sure. But he will be talking about.
I think I'll use it today.
Okay. But what he will be talking about is the concept of using native modules in MicroPython, but being able to compile in from a number of different languages, compiling down to WASM, and compiling down to C, and bundling it all in a native module in an unholy mess. So I'll hand it over to Volodymyr. Thank you for talking, Volodymyr.
Yeah, I think we can have some kind of... Yeah, thanks. Actually, we can have some kind of discussion. I'll be showing some stuff. Feel free to ask any questions. I've been working with WebAssembly for quite some time, like maybe for 4 or 5 years. So I was also, when the WASM appeared, I was wondering if that could be used somehow in embedded software scenarios. And WASM is not typically, back the time, it wasn't considered, very seriously in that context. So I was trying to understand how, or if we could kind of get WASM running on microcontrollers, and that's how, basically I was tinkering with it. I developed a WASM 3 engine, which is kind of an interpreter, but then over time, I also found there is actually a real, a tool that allows you to translate WASM binaries into C code. And I was really excited to see that. And actually, I was able to, even maybe 3 years ago, I was able to compile and build actual modules, like firmwares that were that were assembled with additional WASM conversion steps. I was taking a language, like basically any language that targets WebAssembly, and then I was converting those outputs, the WASM files, actually the binaries, to C, and then I was running it on microcontrollers. But then, I'm also working with MicroPython for quite some time, and recently, I found out that there is a way to compile arbitrary or almost any C code to MicroPython native modules, which look exactly the same as normal MPy files. And yeah, that's how the idea was born. So I was basically trying to get WebAssembly working on MicroPython in a form of MPy modules, and I think it's a success. So we are currently able to build actual applications and run them like that. So I can share my screen now, I think. Do you have any
Volodymyr, sorry, just quickly, does everyone know what WASM is? I just realized that maybe no idea. Do you want to give a really quick what is WASM for folks that may or may not know?
So WASM is, it's a web assembly. So it's some kind of a bytecode that was designed for a web. So everyone probably knows you can run JavaScript in a browser, right? But then JavaScript has, it has its own dynamic characteristics, and it's JavaScript. So it's typically a text file that browser uses to to run some code on the web page. But actually, this basic JavaScript imposes several limitations on how applications can be used in the web. For example, anything that you want to run on the web would have to be compiled or translated to JavaScript, which is a text file. And then you need to load a text file, you need to parse it, you need to do a whole bunch of stuff, including dynamic optimizations in runtime, just to make a simple hello world page that does JavaScript. But actually, there were many attempts to use these translation steps to actually run huge software packages, and basically you could take C code and then translate it to JavaScript just to run it in the web browser. And it worked, but also JavaScript has its own dynamic characteristics, how it works and how it runs, how the JavaScript engine works in the browser. So over the time, the concept of just basically building statically compiled languages into some kind of a binary format that would be compatible with the browser would ship with an engine, a special engine that would load those files, and that concept developed over the years, and now we have this resulted in basically WebAssembly support in all of the major browsers. This is a standardized like W3C has accepted it. It's now available in every major browser. The WebAssembly is a way basically it enables a few things, but major benefits from using WebAssembly. I think this is it allows you to build statically compiled languages, statically typed languages into native code. Basically, it's not like it goes through this WASM intermediate bytecode representation, but then on the browser side, it gets compiled down to native code. So this allows you to run at near native speeds in the browser, and it also eliminates some of the dynamic characteristics of JavaScript. Like basically JavaScript always uses garbage collection. JavaScript always does dynamic typing. JavaScript does a lot of things. So WASM allows you to get rid of these things that are unneeded in many scenarios for many languages, and it boils down to basic bytecode that is it may be even rather similar to what MicroPython bytecode looks like. But today we are talking about compiling those kind of apps to native code. So we are not compiling WASM to MicroPython bytecode. We are compiling a WASM to native target instructions, and then we are running it on actual hardware. Yeah, I think that answers it. So let me share my screen. I hope I can do that.
Okay, go ahead.
Give me
It's
a sec.
also not just about while you get all that sorted out. It's also not just about running in the browser. You can also run it in like sandboxes on a computer, and so there's a bunch of effort into it. There's a WASI effort which lets you host a WASM application sort of on a computer, and so it's almost like a cross-platform, quite fast programming language. So we can talk about it more if it's not that familiar to you guys.
Yeah, so you can find WASM 2 MPy on GitHub.
Congratulations for being on the front page of Hacker News today.
Yeah, actually, yeah, quite a lot of interesting stuff is happening right now, both in the native module space and in well, I must admit that this puts native modules ecosystem in MicroPython under some stress. So I think this is one of the challenges, and I think this is one of the benefits of this project. So this is a real life use case for native modules. And it pushes, yeah, it's on the edge of several different technologies like WASM and native modules on MicroPython. So unfortunately, not everything is working quite well right now. There are some culprits, there are some, difficulties in several corner cases, but overall, I think we can run many languages with this approach on almost any architecture that MicroPython supports. I think there will be more added in future, but for now, Yeah, you can use this repository. You can actually build it on your machine. It does require some environment setup, so I'll be showing a few things throughout this demo. Interestingly, you can see that we can actually have different languages compiled to WASM. And let me show a little diagram. Yeah, okay, so as I mentioned, the idea was actually developed a long time ago. So this was published okay, I think I lost control over my browser. It's frozen. Okay.
Not a WASM-based page, is it?
Yeah, this one works. That one doesn't. Okay.
Good.
So I'd like to show this kind of diagram. Wow, the window manager is kind of freaking out. Okay, so basically you can take any of the supported languages that can produce WASM bytecode. You use normal WASM toolchains for those languages, and it also typically includes the language runtime inside of the WASM bytecode. Then we can run it through an external utility, which is wasm2c in this case, and we get auto-generated C code. But then we can use the native platform toolchain. So this may be GCC or CLang, and we can link in, compile in some platform API glue code and something WASM runtime for a few things like memory management, something like that. And then boom, you have a native binary. And that was developed like in 2021, I guess. But look, in MicroPython context, this native binary is an MPy file. And then you can load it, normal, like a normal Python module and use it. So let's do just that. I have an ESP32 board. I'll plug it in. Okay. I'm not sure if I can switch to, yeah, this one works. So, yeah, okay. So this is WASM to MPy. The environment is already configured. This typically includes like basically downloading the tool chains and some external utilities, WASM to C and stuff like that. But once that's done, we can do several things here. First of all, I'd like to show how I'm testing it because there is a matrix of different builds. And WASM to MPy comes with some interesting infrastructure. So let's just build all. It does a parallel build of all of the supported examples and platforms. It takes around 20 seconds, I think, but let's check it out. So what it does is actually builds a matrix of, every possible combination of WASM apps. Let's check out which WASM apps are available. Okay, it may be tricky to get. Okay, let's get back to the I wanted to show how these apps actually look like, but unfortunately, I think I'm out of control of my browser. Maybe I should just
restart it. Be fine.
It's not working. Anyway. Okay. The build is finished. So let's, work this way. So as you can see, I can currently build every possible combination of my sample applications and architecture supported by native modules.
Oh, yeah.
So build completes fine. Some of these combinations actually don't run correctly, but the combination is working. Let's clean it up a bit. Let's try running actually some of these applications on MicroPython, but I'd like to show the actual WASM apps that we are building. These are located in the test folder, so you can see WASM files, but these are binary. So it would be hard to understand what's in there. Let me try to, maybe I'll try to navigate, because I cannot even close this window for some reason. Anyway, let's get back to WASM apps. Nope. Let's try to use another browser. No. Let's do a new window. No. Okay. I think I'll do some, I'll do some magic.
If in doubt, kill all nine. Yep.
Yeah. Let's do some command line magic and hopefully it gets fixed. Okay, this one is not the one I wanted. There. I think I'm having troubles with basic.
Always happens when you try to do a demo.
Okay.
Why not just log out and in again? I think we can wait this 30 seconds. When you close your session and you log in again, then I think the
I'm
browser
fine. I
is
think
okay.
figured out. So let's get to embedded WASM apps. So this is the source of all these apps that I was running. We can get into apps. Now let's check out, I don't know, Rust. So the Rust app is actually, I was basically creating very simple applications here. So this mimics Arduino code in a way. So there is a setup function and there is a loop function, which the setup just brings something onto the screen and configures an LED. And then loop is basically blinking an LED and printing something. And it does some more tricks to do formatting and printing actual millis on every loop. So it does some more dynamic, like accesses the memory, does more dynamic stuff than just, calling a function. So yeah, that's very simple. It also uses a wiring. Wiring is also a small, interface code, which describes, it's like a binding, I'd say. So it describes external functions and provides some glue code on how to actually call them. But this is typically, the source language provides all the means to do to import functions from the external environment in WASM. So we can see that there is some kind of a dynamic linking happening at this stage as well. But once this is done, we can get to, these WASM files compiled by native toolchains of every language, and we should be able to run it. Let's do it. Let's run all these WASM files on ESP32 S3. So for that, I'm okay. I'm just running tests. I'll check out. Let's check out what the script does, because it might be interesting. So as we can see in the background, it just builds every single application and then runs it on ESP32. And this is a script. So we are looping through all the apps. And if the architecture is not something that we can run locally in the host machine, then we are calling an MP remote. We are just uploading the resulting MPy file, and we are executing. We are importing the module, and then we are calling setup, and then we do just 2 cycles of a loop.
Yeah.
I hope you can see the code.
Yeah, just.
Yeah, so that's just for a test. I'm performing 2 loops. And yeah, we got to the core mark. This is a bit bigger application. So all of these are basically a simple Blynk and an LED. And this one is a bit bigger. It performs an actual benchmark of the code. So see, we have every single application running on ESP32. Yeah.
Really cool. Yeah. There's a lot of stuff hanging together to make all that work.
Believe it or not, I had a basic concept running in a single evening.
Yeah.
And that's huge kudos to native modules, to the, well, basically, yeah, it wasn't that simple. I did a lot of stuff manually, but I just was poking around. I was trying to get it working no matter what. So I did almost everything. Every single command was typed in manually, but it was working. And then I got really excited and I automated stuff. I cleaned up the make files. I did a lot of things to automate it. And actually, there is quite some interesting stuff happening. For example, at one point during this process, I realized that I need to link the compiler runtime, and it's the WASM file is quite big. It uses, especially when you include optimizations, the compiler, the native toolchain will typically do call some internal functions, call some runtime functions to optimize, which are optimized, or which basically implement some of the functionality that is not natively available on the target platform. All these stubs, all these code that is needed to run a native application basically wasn't linked, and I was having trouble to get it up and running. And what I did initially was to grab all the libgcc object files and manually put them into the linker, into the MPy MicroPython linker. And it was a very tricky and exhausting process, I'd say. So I basically ended up with submitting a pull request which implements a static library linking for the MicroPython linker. And I hope this will get merged soon. I'm still not sure if it's going into 1.24, but yeah, I'm here to advocate merging this PR. This will make creating stuff like what I just described much easier. Yeah. So what else did I want to show? Yeah. Are there any questions or like?
I would have some questions.
Sure.
Okay, could you show again this test script, the loop where you run all the tests?
Yep.
So here you have on line 18, you import the module. And
yep.
Line 18. And so when you run this loop twice, a test wouldn't be updated because it's the same module. It's you use the import behavior of MicroPython. So it runs the first time and then you have to reboot the MicroPython. Just that I understood it correct. It's not the force reload, it's just the reload if it was not loaded yet.
I think npm exec will do like reset the MicroPython state, probably. I'm not sure, but
okay.
It works.
Then the other thing is on line 21, you import one app after the other. So all of these apps, these WASM instances will be in memory all one by one. So you had space on this processor for all tests in the memory.
let's try it out. I think
So
we can.
which means these WASM assemblies are really small.
They are. Actually, they are. But the thing is, currently, WASM typically needs to allocate a single WASM page of dynamic memory. So every module that wants to have access to an internal state, that wants to have a memory, it will allocate 64K. So typically, currently there is no way to reduce that, and you must keep in mind that loading every WAS module will require at least 64K bytes.
Okay.
But I assume there is something happening in the background in that script. Like maybe this one is actually resetting the MicroPython state. I guess maybe I'm not sure because I could load multiple apps. It's not actually it's not what I'm testing here. I'm going over the loop of all of the apps and I'm trying to upload these basically MPy files, and then I try to run it, and somewhere at this in this process, I think the MicroPython state is reset, like a soft reset probably happens here, but I'm not sure.
Okay.
So we can do that manually.
And it reboots.
ESPS3, you probably won't run it of it.
Now
You
again,
mean
on
it could be crashing, right?
line 21, line 21. Oh, you just closed the test code.
Yep.
So here you have setup, loop, and loop. These are these you set before the glue code, which is the interface between the WASM and the MicroPython. So you can call WASM this way. Did you also test the callback back into MicroPython or back into
I did. Yeah.
Okay.
If you want to dive into this.
No, don't. I think don't go too far. Just wanted to know if you're working on this.
It is possible. It is possible to call MicroPython functions from WASM. And this is how it's done because see the example applications that I was showing, it tries to call millis and it tries to call pin mode and it tries to print, right? So let me show it happening in that's Viper ID. I'll try to connect to my board. Okay, give me a sec. Okay, I think this may be a bit more tricky. This is Viper ID. Here are all the uploaded MPy files that the test uploaded to the board. I can import, say, C++. And then I can call setup, which does print something, but to print to the terminal, like this printing happens through MicroPython printf function. So we are calling back into in this particular case, we are calling the system function, but there are other cases. For example, if I do C++.loop, you can notice that it does print time, and time is imported from time module. This is also C, but I could easily import Python, another Python module this way and call it. So everything's, it fits nicely.
Yeah.
Cool.
Yeah.
Really cool.
It's impressive.
I also would like to show you that one of the features of Viper ID, I could disassemble MPy files right in the IDE So I enabled it. And now when I get to the file system, let's check out the SSL module, for example. This one contains the string table, everything this module references to, and then there is some bytecode in there, so you can actually read through bytecode, which is MicroPython bytecode. But if we try to open the C++ MPy, we can see that, okay, the string table is there.
Yeah.
There are exports, there are imported functions as well, but there is no Python bytecode. Everything like is native code here. Yep.
So if you wanted to call a Python function from Rust or from C++, how do those environments, how does that work?
So currently you need to create some glue code. Currently you need to okay, I can show this portion of the source code, and you'll realize how easy it is from one perspective, and maybe also what's needed to make it even more easy. So right now, if you open wasm to MPy repository, you'll see there is a runtime directory and there is a runtime.c. This implements all the glue code that is required to bind MicroPython with wasm. So we can see that the setup and the loop functions are pretty trivial. So they basically just forward the function call to the wasm function, and that's it. Now later on we expose setup and loop functions to the runtime, to the to the MicroPython attributes of the module. But this is it. So it's really easy to call. Well, in some cases it may be more tricky because you need to also create code that passes arguments around, but that could be auto-generated. So I think one of the next steps for this one would be basically based on the wasm file that we have on the input, we could auto-generate these functions, like the wrappers for these functions. It should be pretty easy to do because wasm contains all the type information needed to generate it, and the typing system of wasm is pretty simple. So it's basically native types like integers and floats, so nothing fancy there. Now for instance, we also want to provide some functionality to our wasm file, like basically to provide a delay function. This could also be somewhat automated, but for now this needs to be hard-coded. So you can see that when the wasm file is trying to, with the wasm app, is trying to call delay in the wiring module, I'm forwarding this call to the MP sleep MS function, which is an object that I got from the time module, which is imported. So basically I do dynamic import of the time module, and then I grab the sleep function and grab the ticks function from there, and then I use these to provide the required functionality to my wasm app. So this whole file is like 128 lines of code. I like this number.
Yeah.
Yep.
There is something interesting on this file. Just go to the second line. You
Second
created
line?
it the second line, you created it yesterday, or I'm wrong? No, it was a month ago. It's very fresh. It was a month ago, huh?
Oh, this is
Yeah, and I've not
Okay,
been working
cool.
on this maybe 2 or 3 weeks. I mean, like previous weeks. So I was mainly focused on linking on the linking pull request for the static library files. This is pretty pretty much finished. So I besides like doing some automation, auto-generating some parts of this code, or doing crazy stuff like that, this is pretty usable.
Yeah. That's cool. I think Damien's joined in now, so you can make the case to merge your PR to him.
Sorry, I didn't get it, I guess.
So I think Damien's joined, so you can make the case to merge your PR.
Yeah, I think I think we'll get there. But yep. What I'm thinking about, currently from the compilation perspective, everything's fine. From the glue code perspective, it looks neat and tidy. So that's as I said, that's a huge kudos to the pre-existing infrastructure in MicroPython that was leveraged to make it happen. But in runtime, we do have some issues. So some of the combinations of platforms and apps are just not working yet. And I think it may be due to some of the existing tickets. So I'm waiting for some bugs to be cleaned up, to be closed. And then I'll be rerunning this test from time to time to, just to keep track of the health of the system. And I really hope the pull request that implements linking of static libraries will be accepted soon, because it just simplifies creation of these kind of projects. It was like a huge mess. It was it's really hard to get the idea right of what you have to do to pick the correct object files and how to. So you're basically doing part of the work that should be done by the linker, that you typically expect the linker to do. Okay,
We've got
that's
pizza
it.
here. We got pizza here, but we'll have to wrap up for now. But that's really cool. Was there any other things you wanted to quickly cover, or?
No, that's it. Unless there are any questions.
Now, one very small thing. The very typically use case for this. So if somebody would like to write something in Go and has a WebAssembly, and somebody would like to use this WebAssembly in MicroPython, that could be, I think, one use case. Or do you have special use cases in mind?
Yeah, there are many. There are several use cases actually. This allows you to run other languages as MicroPython like modules. Basically, it allows you to run this code pretty fast. So it's not near native right now, like near native speeds right now, but I think there is a path to get to a point where this code will be running at near native speeds, and that leads to this dilemma, I guess, because MicroPython, from time to time you can hear that MicroPython is slow, right? I think this is a bit exaggerated, because MicroPython is slow, but it's slow for typical computational tasks, CPU-bound computation style stuff. But typically you won't experience the slowness in I don't know. I'm like working in IoT space, right? And in IoT space, typically many operations are IO bound, so MicroPython overhead is negligible in that case. But what if, for example, I'd like to run an AI model, right? Or a computational algorithm that crunches numbers. Okay, I could resort to writing native or assembly functions in MicroPython, but what if this code is already written or maybe I just, prefer using some other language to implement it. So that way I'd be able to, well, first of all, this is code reuse. So I can develop and debug code on the host, right? And then I can almost automatically convert it into an MPy file and load it and use it in MicroPython. I think that this is, the biggest motivation is to reuse code and to be able to run it fast. So yeah, I think that's it. I can also show that the produced MPy files are rather small. So see the Rust is like 20K, but most of the others are below 10K. The C++ MPy file is almost 4 kilobytes. So these are tiny.
These files contain the runtime.c, which you showed us before. All of them contain it, huh?
Yep.
Okay.
So these files contain the runtime, like the WASM runtime. They also contain the compiled code, like the translated code. I think I can show how this code looks like, but let me then do. Okay, I'm not sure I'm prepared to do that, but I can do a trick. So let me modify my run tests. And I'll just leave a single application in here. Let's pick assembly script. And now I can run it. Okay, I'm not sure why it wasn't run, but my main idea was to open up the wasm.c file, which is auto-generated code, which the wasm file gets converted into, and then this file is then compiled via native toolchain and it's linked basically into the MPy file along with the runtime. So this is an actual app, and I can scroll down to, I can scroll down because I want to skip all the boilerplate code in that auto-generated things, and here are the actual functions. So this is basically assembly in a C syntax, and that's what we are getting as a result of converting WASM to C.
Cool.
All of this code is linked into, along with the runtime, is linked into the MPy file, and we are getting this tiny, like 10 kilobyte package.
I like it. I like it a lot. It's really cool.
Yeah.
Cool.
Well,
Thank you
it
for that.
stands on the shoulders of what was previously done by the community, also some of my, previous works. And now I really like it because typically if we are doing it for other targets or for other systems, you'd have to link that runtime and also link the WASM file into the whole, like into the binary blob of the firmware. And on ESP32, you'll be getting a 1 megabyte file. So basically it would include everything, like the Wi-Fi stack, the Bluetooth stack, all the crypto stuff, all the drivers, everything goes into a single blob. But in MicroPython, thanks to the dynamic modules, we can have a separate small file that we can, it provides a lot of flexibility, and it provides benefits to me as a developer, because I can take this small file and then ship it over the air in a matter of seconds to my board or to a fleet of devices. So this is really cool. This enables new scenarios in IoT space as well. Okay, thanks. I think that's it.
Thanks very much, Volodymyr. Thank you.